Hello and welcome back. We're going to go through questions 6 to 10 of the SMO Open mock paper. As usual, you can find the link to the problems in the description below if you haven't tried it out yet. Let's begin question 6, which is our first combinatorics problem. We have a diagram here where you're supposed to find the number of paths from A to B. And from A to B, you're supposed to use exactly two of these diagonal shortcuts, but otherwise just go downwards and to the right. Now, the first thing for such questions is that if you're unable to solve it straight away, try to solve a simpler version of the problem. And the simpler version of the problem perhaps would be if this line were drawn in. Now, how would we solve that version of the problem? Well, we cannot count the number of ways in the usual fashion because there are two diagonal shortcuts. So instead, what we can do is to think of what is the collection of moves that I'm going to make in order to get from A to B. Now, from A to B, it is 7 by 8. We know that there are two of these diagonal moves, which means that you still need to go to the right 5 times and downward 6 times. And any arrangement of this would give you a path. You are never going to actually walk out of this because you take a total of 7 steps to the right and 8 steps downwards, which would get you precisely to where you want. So the number of ways to arrange this, 13 moves, divided by the 2 factorial, 5 factorial, 6 factorial in the repetitions. And this is pretty large. It starts off at 36,000 paths. That's not the answer because some of these paths are going to go through here. So we need to subtract off those paths that do go through there. Now the question becomes, out of these 36,000, how many of them actually go through that forbidden, non-existent shortcut? So let's draw it here. And the question is, how many paths go through that? Well, for you to go through that, it means that you must have gone from A to one end of the shortcut, taken the shortcut, and then after that gone to B. I'll call this to C and D. So there are two different ways in which this could happen. The first way is that you went from A to C with the shortcut, and then after that D to B without the shortcut. In this case, if you went from A to C with the shortcut, it means that you would have gone 3 down, 3 right, and the shortcut. And then from C to D, and then from D to B, there's no shortcuts left, so it's just 3 down and 2 right. So here we can count it, 7 factorial over 3 factorial, 3 factorial, multiplied by the one at the end, which is 5 factorial over 3 factorial, 2 factorial. If we compute this, this gives you 1400 paths. And that's the other case where you go from A to C without the shortcut, but from D to B you use the shortcut. This one would be just a touch different. The front half would be 8 factorial over 4 factorial, 4 factorial. And the back half, you would now be using the shortcut, so it is only going to be 4 moves. 1 shortcut, 1 to the right, and 2 downs. So 2 factorial there. And this is 840. So all we need to do is to take 36036 and subtract off these two numbers. So subtract off 1400 and subtract off 840. So the final answer would be 33,796. Now, my tip would be that if you do a problem like this, double check your calculations again, because there are 5 of these factorial expressions where you may have counted something wrongly, or you may have multiplied something wrongly, or you may have subtracted wrongly at the end. So double check it, because these are very mistake prone kind of calculations to make, and even if you make one small mistake, your answer will be wrong. So do check it again. Okay. Next up, question 7. Let CD be the diameter and AB, EF be chords parallel to CD such that AB equals to 12 and CD equals to 20. So the diameter is 20 and this chord is 12. Given that ABE equals to 45 degrees, determine the area of ABFE, which is a trapezium. Now, the most useless looking condition here is the 45 degrees, and that usually means it's actually the most useful. The 45 degrees in and of itself isn't that informative for this problem, but if we were to draw it into the center, which is on the diameter, it means that the angle at the center is 2 times the angle at the circumference, which in this case tells you that this would be 90 degrees. And obviously, having drawn these in, we know that they are both going to be of length 10. Now, with the center included, I can further draw in the line connecting A, B, and EF, the heights of your trapezium. And because it is in a circle, by symmetry, this is going to be 6 and 6. So we have a 3-4-5 ratio. 6 to 10 is 3:5, so this should be 8. Now notice that since we have drawn this height in, the only thing that we are left to find is information about the right half of the diagram. But actually, these two triangles are congruent to each other because of the fact that the two angles here are complementary. You will actually get congruent triangles. They have one equal side length, which is the radius 10. So therefore, this would be 6, 8, and 8. Okay, now we have got all the lengths we need, so this is just the area of the trapezium. So half times the height is 14, two bases are 12 and 16. And the area is equal to 196. Question 8. Let P of x be a degree 4 polynomial such that P of 3 equals to 144 and x minus 8 px equals to x px minus 2. Find P of 3.5. It may be tempting to put in 3. And if you put in 3, you would be able to find something like P of 1. From P of 1, you could find P of negative 1. But you know that you're just going to keep on finding all the odd numbers. You're never going to get 3.5 to show up. So doing that sequence of substitutions will give you some values, but it's never ever going to give you P of 3.5. And similarly, if you keep on putting in 3.5, you'll relate it to 1.5, negative 0.5, 5.5, 7.5, but you're never going to get it to 3. Now, instead, what we can do is to say, I only need to find out what are the roots of my polynomial. And if I find out what are the roots of my polynomial, then I would know what it is, because this is a degree 4 polynomial. So let's put in something like x equals to 8. And you put in x equals to 8, well, you get 0 equals to 8p of 6. So p of 6 is 0. Well, then I should put in x equals to 6. If x equals to 6 is put in, the left-hand side is going to be 0, because p of 6 is 0. And so now you get 6p of 4 is 0, so p of 4 is also 0. And likewise, you can repeat this and you would get another root, 2. And do it again, you get another root, which is 0. At this point, you have found 4 roots for a degree 4 polynomial. So there shouldn't be any more. And indeed, if you tried to put in now x equals to 0, you would get 0 equals to 0. So that's a good thing in the sense that we haven't done something wrong here. It is really a degree 4 polynomial with these 4 roots. And there isn't any reason why there would be a 5th root. It shouldn't exist. By our factor theorem, it tells us that the polynomial p of x should just be a constant multiple of x, x minus 2, x minus 4, x minus 6. What multiple? Well, that's why they give you one value, p of 3. And that p of 3 is actually otherwise irrelevant, but here it would give you the value of c through the substitution. So 144 equals to c times 3, 1, -1, and -3. And that gives us c is equal to 16. So finally, to get p of 3.5, put in 3.5. 3.5, 1.5, -0.5, -2.5. You can multiply 2 to each of these so that it is easier to compute. 7, 3, -1, and -5. And so the final answer is 105. Yeah, now the degree is a very underrated piece of information whenever you're working with polynomials. Remember that once you know the degree of the polynomial, you know how many roots it has. And conversely, that means that once you know the roots, you know practically everything about the polynomial. So that's why an information like degree can be very important in letting you know when you have got enough information to pin it down precisely to this point where it just differs by a constant multiple. Question 9 is one of perhaps 2 questions that I said which are deliberately not very nice. Now, when I say deliberately not very nice, that's not to say that you can't solve it. It's just that it does involve a bit of tedious casework, guess and check, and you can't really improve on that. Now, unfortunately, the SMO Open has had this habit in recent years that there is 1 or 2 of such problems where it is just tedious. But that's also a good thing in a way if you are completely stuck and you just want to spend 10 minutes thinking about something like this, you would be able to solve it. Okay, so x and y are positive integers with 20 and 22 factors respectively, and x times y has exactly n squared factors where n is a positive integer, find n. That means that you want to find x and y such that it has a product with a square number of factors. Now, there's nothing significant about having a square number of factors. A square number has an odd number of factors. But a square number of factors doesn't really mean anything at all. So the only way that we can do this is sort of manually, looking at what kind of prime factorizations could x and y have. with 20 and 22 factors? Well, you have a couple of choices. It could be a 19th power, although that seems really unlikely. 20 is 2 times 10, so it could be something times another thing to the 9th power. And 20 is also 4 times 5. And 20 is also 2 times 2 times 5. So you've got these different forms of your prime factorization that it could potentially be equal to. Just write that a bit more clearly. And now we will do the same thing for y. Y could either be, I'll use ABC here to contrast that PQ and R's may not be the same in these two scenarios. But they could also be the same. We're just not sure which one should overlap. So it could be 21 or 2 times 11, meaning that it could be A times B to the power of 10. Now we need to overlap these prime factors and to overlap some combination of them so that you exactly get a square number of factors. So you can think of it almost as these are just different combinations of numbers and you would like to combine some of them. So you've got either 19, you've got 1, 9, 3, 4, and 1, 1, 4. And down here you have got 21 or 110. Now you would like to merge together these in some way whereby if you now do the same counting factors approach, which is add 1 and multiply, it gives you a square number. Unfortunately, this is a slightly arduous task because there is no shortcut. The only thing we can say is that for something like 21, it's pretty easy to check because 21 is just one number. So it either merges with the first one or the second one, and you can just check them one at a time. I'm just going to tell you after a few minutes of search what you would hopefully be able to spot, which is that there is a combination that involves the 110 and the 114. And the way in which you would combine it would be like this. So, in other words, the power 4 would combine with the power 1, the power 1 combined with the power 10. So you would get something like p to the 5, q to the 11, and r to the 1. So the number of factors of this is going to be a square number 6 times 12 times 2. Okay, so square number and n is equal to 12. Now, if you're wondering, how do I know that there isn't anything else? The truth is that I just checked everything. There is no shortcut for these kinds of questions. So I don't like setting problems like these too much, but I think it is about representative to have 1 or 2 of such problems in a set of 25. So here we have it. But the good news is that if you are taking the SMO Open, you don't have to worry about, is there another one? Because there should only be one answer. So once you find one of them, you know that must be the one. So you don't have to worry about that. I have to worry about that when setting the question. Okay. Last up for this video is question 10. And you have this rather amusing looking thing that looks like a typo. After they tell you that the sequence A1, A2, A3 is an arithmetic progression of positive integers, you're told that A102 is 2022. And this, of course, looks like an error because things normally go up, they don't really go down. Right? When it goes up, they are just a stack of powers. But what is A102? Well, it literally means that. So it's A of AAA102, and AA102 is A of AA102, and AA102 is A of A102. And I'm already running out of space to draw the brackets, but you know what I mean. Now, the point here is more that we need an efficient way to express this. And so I'm going to write it in this way. The arithmetic progression has a common difference and a first term. I don't really need the first term. I'm just going to write it as dn plus x. And d is the common difference. We know that this common difference is positive because the whole sequence has distinct positive integers. So it must be going up. If it goes down, it will eventually be negative at some point. So the common difference must be greater than 0. And we also know that since the whole sequence is positive, that includes a1. So x has to be more than negative d. Okay? Otherwise, your a1 is going to be 0 or negative, which we don't want. Now, one way that you can interpret this is that any sequence an, A is actually a function. A sequence is just a function whose domain is the natural numbers. That's all it is. So A is kind of like a function named A being applied 4 times. And so if we apply this 4 times to A102 specifically, you're going to get, so A102 is 102d plus x. And then you're going to take A of this. So AA102 is this whole thing times d plus x. And then you're going to do this again. Sorry, not plus d plus x. So you do this again, you get 102d cubed d squared x dx plus x again. And then finally the 4th layer. There's not much mystery here anymore. It's just write it down very carefully. Make sure you don't miss any terms when you're multiplying by d plus x. I'm going to clean it up a little bit because only the first term doesn't have x. Everything else behind has x multiplied by an increasing power of d. So d cubed d squared d plus 1 x. And this is supposed to be 2022. Now this doesn't look like an equation that can be solved very easily, but remember that d and x are both integers. D is a positive integer and x, well, manner of speaking, can't be too negative because x is greater than negative d. So this means that d certainly cannot be too big because whatever you have down here, the most that it can subtract off is if x is negative d. This whole thing here subtracts off at most, very loosely, 4d to the 4. So it means that you need your 98d to the 4. This is the smallest it can go. So it has to be within 2022, which is very strict. Because if d is equal to just 3, 3 to the power of 4 is 81, and 81 times 98 is far bigger. So d can only be 1 or 2. And once you have that, it is pretty easy to calculate. If d is 1, then x is just going to be 2022 minus 102 divided by 4. So in either case, just substitute and check. You will get x is 475 for this case. And I chose the coefficients so that when d equals to 2, there's also a solution. When d equals to 2, x would be 26. So your two possibilities for A 2022, A 2022 is 2022d plus x. It's either going to be 2022 plus 475, which is 2497, or 4044 plus 26, which is 4070. So the sum of these two would be 6567. Alright, that's taken us up to question 10. If you've done many of these questions correctly already, that's a very good job, because for the SMO Open, if you get something like 12 questions or 13 questions, you are on the cusp of being in the second round. So many of these problems in the first half are where you would hope to get most of those marks. Right, so thanks for watching. Please subscribe if you haven't already, and look out for the remaining videos on this mock paper.